Energy is the most important challenge facing our society today. We're going to need to replace 85% of our primary energy supply in the next 30 to 50 years.
Enter the organic solar cell, subject of a great deal of research and interest.
This lamp is a mimic the sunlight, so you can turn on the sunlight, then the polymer solar cell will convert the sunlight into the electricity to power the fan.
What's cooler than having a thin piece of plastic that turns sunlight into electricity, that can power your lights, your refrigerator, even charge up your electric car at some point in time?
Flexible solar cells made from organic plastics are lighter weight than the silicon solar cells we use now. And they're potentially less expensive to make and install, but they don't work quite as well, yet. Researchers at the University of Washington are looking at ways to make those thin films more efficient in converting light to electricity. The structural elements they're studying are on a nanoscale level, about 10,000 times smaller than a human hair.
It's how those features are aligned, how they're ordered, that controls the performance of these cells.
While chemistry department researchers determine how charges are transported, the materials science and engineering department looks at ways to design and manufacture a usable and cost-effective product. The goal is to be able to print large sheets of plastic solar cells using technology similar to newspaper printing.
From the economical point of view, okay, this can be potentially very cheap, okay, and potentially can be very cheap to operate also.
Right now, the cost of solar energy is not just the materials cost of the cell. It's the cost of the installation. And so the vision is we've got these plastic materials. The material cost is lower. They're lighter. They're flexible. The installation costs can potentially be much lower as well. You don't have to reinforce your roof. You don't need a metal frame. You don't need standoffs. So all of these associated costs can be driven down as well with these new thin film technologies.
This will be dramatic impact not only to economy but also to the environment. Okay, so this is dramatic, I think, the impact to the societal.
Good evening. My name is Alvin Quorum, and I want to thank you for joining us this evening. I also want to thank the University of Washington Alumni Association for their support in publicizing this event. The UW Alumni Association, the College of Engineering, and the College of Arts and Sciences have joined forces to sponsor this evening's activities. So please join me in giving them a hand. As you listen to the presentations, I invite you to write your questions on the cards that you received when you came in and pass them to the aisles at the appropriate time. We'll try to get to as many of those questions as we can during the panel discussion. For those of you who are under 30, you may want to use Twitter by using the hashtag #NewDawn. It's on the pencils that you also received. But please silence your phones. As Professor Ginger said in the video, developing clean, renewable sources of energy is one of the most urgent challenges of this generation. And yet, there does not seem to be a sufficient appreciation for how difficult it will be to meet this challenge. We have taken our fossil fuels too much for granted, but they are not forever. What has taken Mother Nature millions of years to produce, we have essentially burned up in my lifetime. Dean Kause will give you a quick overview of the scale of the problem, which I think you will find sobering. So we need to change course. We need to become much more serious about sustainability. We need to develop all practical forms of renewable energy, including wind, biomass, tidal, and others. Research on biomass and tidal is also going on at the UW in the new College of the Environment, although we won't have time to discuss that this evening. Our focus this evening is on solar cells and related technologies. Solar energy is forever. It is a unique resource, and we need to exploit it with a heightened sense of urgency. There are a couple of key concepts that are worth noting. First, a basic question to ask about any energy technology is, Can it be scaled to meet the global need? The numbers that describe our global energy consumption are staggering. It's a bit like our national debt. The term trillion, or tera in scientific lingo, is becoming all too familiar. We need to come to grips with what it will take to provide alternative energy sources at this scale. Dean Kause will give you a sense of the scalability challenge. Second, our current solar cell technologies face significant scaling and cost challenges. But the future looks very promising, thanks to some revolutionary advances in molecular science and engineering. The focus of much of this work is at the nanoscale, namely about 1 billionth of a meter. Dean O'Donnell will highlight some specific examples of research at this new frontier. Finally, I would like to emphasize how critical your engagement on this topic is. Without strong public support, there will not be the political will to give this issue the attention it deserves. So after the main presentations, our distinguished panel will discuss how we might accelerate the progress in this area, and President Wise will suggest how we can all work together to tackle this task. And now it is my pleasure to introduce our keynote speakers for this evening. Anna Marie Kause is the Dean of the College of Arts and Sciences and the Earl R. Carlson Professor of Psychology. Arts and Sciences is the largest college in the university, with about 40 departments serving over 20,000 students each year. Anna Marie herself is an outstanding teacher, having received the UW's Distinguished Teaching Award in the year 2000. She also received the Distinguished Contribution Award from the American Psychological Association for her work on youth growing up in risky environments. Professor Kause served as chair of the psychology department, and most recently, she was the executive vice provost, a post she held until becoming dean in 2008. Matt O'Donnell is the Frank and Julie Jungers Dean of the College of Engineering. Matt joined the UW as Dean of Engineering in 2006 after serving as professor and chair of the bioengineering department at the University of Michigan for 7 years. During his career, he also spent 10 years in the corporate R&D center at General Electric. A physicist by training, he has over 300 publications and 55 patents. In 2009, he was elected to the National Academy of Engineering. We will begin this evening's presentation with Dean Kause.
Thank you very much, Alvin, and good evening, or given our theme tonight, maybe I should say good morning. It's a pleasure to be here tonight, side by side with my colleague Matt O'Donnell, the Dean of Engineering. And over the last few years, we've been talking a lot about how our colleges can partner to tackle the big problems of our time, like energy. Energy is as essential to life as is oxygen, water, and food. Finding a way to meet the world's growing demand for energy in a way that's sufficient, safe, and sustainable is one of the defining problems of our time. Solving it has important consequences for world peace, for dealing with global poverty, global health, and for preserving our environment. Our society has become much more mobile, and the need to find alternatives to fossil fuels is critical. Attacking this problem is going to require a vast range of competencies in science, in technology, in engineering, and also in public policy, commercialization, business, and philanthropy too. And it will also require a commitment amongst all of us to work together, locally and globally. What could be more important or more fun? Our focus tonight is going to be on the use of molecular science and engineering to design and manufacture new advanced materials that can help us achieve this new dawn for solar energy. Now, there are many reasons why we need to decrease our reliance on fossil fuels. My hunch is if I asked most of you why we should do this, many of you would talk about pollution. Or you might mention environmental calamities like the Exxon Valdez or the oil spill in the Gulf. Or you might talk about climate change. These are all good reasons to be concerned about our reliance on fossil fuels. But it's more than just about the environment. It's also about national security and our dependence on governments that are autocratic and unstable. The events of the last few months, and those that are still very much ongoing around the world, should have us thinking twice about relying on others for something that's so essential. And then there's the price of gas. It all comes down to the simple issue of supply and demand. When it comes to our energy needs, these two forces are on a collision course, a collision that will likely occur in our lifetimes or those of our children or grandkids. To get a sense of the magnitude of the problem, let's look at current energy consumption. Energy consumption in the world is about between 16 and 17 terawatts. In the US, energy consumption is 3.3 terawatts. Now, I find terawatts difficult to wrap my mind around. So how much is 3 terawatts? Well, it's like if each of us kept 110 100-watt light bulbs burning 24/7, 365. That's a lot of light bulbs. And energy demands just keep on increasing. There's roughly been a doubling in world energy consumption since the oil crisis in the mid-70s, and it's expected to double again in the next 30 years or so. Now, we can argue about the date. Different groups have different estimates, but there's no argument about the basic facts. Fossil fuels are finite. Our need for energy is not. The collision between supply and demand will come to a head even if everyone in the US gave up their car right now and walked every place. Right now, the US is about 5% of the world's population, but we use about 20% of the world's energy. We in the US have tripled our energy consumption since 1950. But China has doubled its consumption in just the last decade. In 2010, China became the largest single consumer of fossil fuels. But if you look, their per capita consumption, or that of India, is still quite low. That will change. At present, almost all our energy comes from fossil fuels: oil, gas, coal, and about 9% comes from nuclear energy. So our energy demands are increasing, supplies of fossil fuels are diminishing. The collision course between supply and demand is building. The crash will happen unless we do something different. So what to do? The answer is actually pretty simple: renewables. That's the obvious answer. But right now, renewables account for only about 8% of our energy use. That's predominantly biofuels, hydropower, wind power. Solar is only a sliver, about 1%. Remember those 110 light bulbs that we talked about? Well, only 8 of those light bulbs are turned on by renewables, not even one of them by solar energy. We can change that. We must change that. Increasing that percentage is exactly what our scientists and engineers are working on. It's one of the most important challenges of our time. Meeting it can help secure a positive future for humankind and for our planet. We need renewable energy, and we need to develop it just as rapidly as feasible. there's no silver bullet, and developing all sources of renewable energy is good and worthwhile. We need about 3 terawatts. So what would it do to get a third of that from various sources? So let's look at biomass. Biomass is good. We should support the development of biofuels, and we have some excellent scientists right here at the UW, also at WSU, that are doing wonderful work in that area. But there are some very significant scaling issues. To meet about a third of our energy needs from biomass, that 1 terawatt, it would require about a quarter of the continental US landmass devoted entirely to energy crops. Biofuels are important. We need them, but they're only part of the solution. How about wind? Wind is good, and I love the Connecticut art forms that we find with wind farms. But to get to a terawatt, it would require wind farms equal to an area larger than the state of California. Even more important, if we were going to try and get the full 3 terawatts from wind, we'd have to use all the production capacities in terms of US steel and cement production for 15 to 20 years just on building windmills. Wind is good. We need wind, but it's only part of the solution. So how about nuclear? We've been hearing a lot about nuclear lately, been getting a lot of attention. And before the tsunami in Japan, there had been plans for hundreds of new plants around the world. But to get to that 1 terawatt of power from nuclear, we'd need 1,000 or almost 1,000, not 100 new commercial reactors. And the enthusiasm for doing that has diminished. Now, some have been talking about developing small, standardized reactors. I think it's a great idea, and I'm very interested in seeing how this develops. I think nuclear needs to be part of the mix, but it's only part of the solution. In fact, we'd be silly not to develop every source of energy that's feasible. Biomass, wind, hydro, tidal, nuclear, all should be part of our portfolio. But solar needs to be a much bigger player than it is now. So how about solar? Well, using solar cells with about 10% efficiency, which we're at now, an area of about 10,000 square miles would be sufficient to generate 1 terawatt of electricity. Now, that's a pretty large area, but it's much smaller than what we've been talking about with biomass and wind. And it's roughly equal to the already existing area of rooftops and roadways in the US. Okay, right now, you fly into Seattle. I think President Weiss flew into Seattle just a little while ago. And you see miles of roofs. These roofs are flanked by green lawns and trees. But to our engineers and scientists, these roofs look like a vast, underdeveloped resource. The sun's energy keeps the grass and the trees growing. Why not use the space on those roofs to energize us humans? Rooftops and roadways are already located where people live. And that's the perfect place to meet local demands. Now, think about how well this might work in remote sections of Africa or Asia or South America, areas that are far from the grid. This could be pretty cool at solving a lot of problems. After all, the amount of energy, the amount of solar energy reaching the Earth in less than 2 hours is enough to meet the energy demands of the entire world for a year. So why solar energy? Well, there's just so much more of it than anything else. It's virtually limitless. Our earliest ancestors knew that the sun was important, They worshiped it. Maybe they knew something. And if you've been watching the weather in Seattle for the last couple of days, the gods are smiling on this event. The sun did come out. And we already have a very remarkable technology that we can use to convert sunlight into electricity. Silicon solar cells, or silicon photovoltaics. And it really is a remarkable technology. It's robust, and it lasts for decades. What's the catch? Well, there's a few problems, a couple of catches here. First, there's the issue of cost. When we compare solar photovoltaics to nuclear, to solar, to fossil fuels, it's just too expensive. Right now, the payback time, or the time it takes to recover investment costs for these silicon photovoltaic installations, is just too long. There's also the issue of materials. For solar to contribute enough electricity to meet US or world demand without creating new national security issues, the materials that go into manufacturing solar cells have to be abundant on Earth, and they must be widely distributed across the geopolitical map. Then there's another kind of gnarly issue, and that has to do with the energy required to manufacture solar cells. This sets a practical constraint on how fast the market can grow without needing to build new coal plants to power the solar cell factories. Okay, so what we need factories. We need the factories to make solar panels, and then we need the solar panels to power the grid, to get electricity to your home, to your cars, whatever. But let's take this example. Okay, let's imagine that we used only energy from solar cells to manufacture more solar cells. Right now, for state-of-the-art silicon solar cells, it would take over 30 years to reach an electrical generation capacity that would meet half of US needs. So during that 30-year period, we would not have generated any solar energy for anything other than making more solar cells. So it's not very satisfactory right now. It's just very energy intensive to manufacture silicon solar cells. The silicon has to be purified, and then there are high vacuum and high temperature processing steps. I think this analogy is apt. Remember the Red Queen in Alice in Wonderland? She told Alice she'd need to run faster and faster just to stay in the same place. Well, with today's solar silicon cells, that's the dilemma we're talking about. Again, 30 years just to produce enough solar cells so that we get anything more than solar cells. But here at the UW, and what's so exciting about tonight is that we're going to be telling you about the fact that we're developing new solar cells that would require dramatically less energy to manufacture. So when we're running as fast as we can actually make progress towards weaning ourselves away from fossil fuels. In addition, we can also gain energy security, and we're not sacrificing economic growth. That's exciting. These new cells, which Matt will talk about in more detail, use very thin layers of the active material. They're so-called thin film devices. They're easy to manufacture because they can be printed from solution. It's kind of like producing color film. Remember Kodachrome? They're also lightweight and easy to install. And these three factors combine to make production a lot cheaper. And scaling up isn't an issue. For example, each year we make enough saran wrap to cover Arizona 7 times. This can actually work. So now I'm going to hand it over to Matt, who will tell you more about developing new materials to make new types of solar cells, both organic and inorganic. He'll also talk about what we're doing to make these cells more efficient and to deal with storage issues. The work going on right here at the UW can make this new dawn for solar energy happen. Take it away, Matt.
So I hope in about the next 20 minutes or so we can have a little fun just to talk about the things that are going on at the University of Washington in these areas. But first I want to set a little context. And the context is a solar cell, and you'll see a bunch of them, by itself is not an energy solution. A system is an energy solution. So let's look at that in this context. And the first is how a solar cell would fit into a conventional energy system as we know it now. And that is that we would create a source of energy, which is the solar cell, which is on your left over there, and it would pump power, electricity, into a grid system, which then is distributed down for use in your house, in your buildings, in your factories. However, you have another capability with solar cells because of this distributed capacity that they have, that you can also, in addition to doing that, you can locally keep the energy by either storing it or directly pumping it into use. Now, why do you want the storage piece that's there? So not just the use and delivery to your house, but why would you want to store energy? The reason you want to store energy is because the light isn't always there. So at nighttime, if you've created your energy from solar power, then how, in fact, can you use it? Well, you can use it by taking off the charge from that storage in the same way you would take water at your tap from a water tower at home and use that. Once you go to bed at night, the system stops, ready for the new day to dawn and to go back to this system. Okay, so the solar cell must fit into a general energy system like this, which has 4 major components to it. The 4 components from your left at the top is the clean energy sources, which are the solar cells we'll talk quite a bit about. But also we need to be able to store that efficiently, and we'll talk about some better energy storage systems. We also have to distribute that energy smartly, wisely, and efficiently, and that's a better distribution systems. And finally, how we use that at the lower left there, how we use that, we want to make sure that all the electrons that are delivered to your house, that they're mostly used for things which you want to do as opposed to just creating heat. So I'll have the pleasure, actually, of going through a collection of work from folks at the UW in these areas. There are many, many people you can see down here. Even I'm barely from here can see all their faces down the bottom. But there's a large collection of people at the university who are working in some aspect of this area of solar energy and solar energy systems. I will highlight an octet up here of people, and just as examples of the type of work that's going on. The first thing that I want to note, though, is that I'm not going to be talking about distribution systems. That is the smart grid component itself. We have a lot of work going on here, but it's not directly related to the molecular engineering, molecular science work of this set of people. So hopefully, maybe in the later presentation, we can talk about the wonderful smart grid work going on at the university. So let's start with first sources of solar energy. And from that, we'll highlight the work of Professor Alex Jen, who's chair of the Materials Science and Engineering Department and also co-appointed in Department of Chemistry. So you can see a lot of slides now about solar cells, okay? So as my friends all know, I tend to get very geeky when I get into these things. So before I get geeky, what I'd like to do is try to just paint a simple picture of how this works. I guess it's a simile. So you can think of a solar cell working like a peanut butter and jelly sandwich, okay? And it actually does. So let's think about the peanut butter and jelly. Besides, actually, I didn't get very many snacks upstairs, so I'm looking at this for later. But in there, that it actually has 3 components to a peanut butter jelly sandwich, right? You have the bread, you have the peanut butter, and you have the jelly. So let's turn it on its side and use this as a simile for what we have in a solar cell. That is our bread, our top and bottom parts can be thought of as the electrodes that are in this system. That is, those are the things that are going to collect the charge that comes out and send it out into our electrical surface and circuits. The photoactive material is the peanut butter and jelly. This is the thing that's going to convert the light that comes in to electricity, which the electrodes will capture and bring out. Why peanut butter and jelly? Why two parts? Because we have two kinds of charge. And so one's going to be associated with the positive, or hole, as we call holes, and the other with the negative charge. The last piece, though, you notice how that top slice of bread's a little funky on that peanut butter sandwich? The reason why is because you have to be able to get light through it. You have to be able to see the jelly on top, because the light has to get into the sandwich for the peanut butter and jelly to do its work. Okay, so let's go back now to the cartoon version of that, and how does it work? Well, the first thing you see here is the top and bottom are the electrodes, and the two pieces in the middle are our peanut butter and our jelly. The first thing is we have to make sure that our top electrode is transparent, but it also must conduct electricity. So I have my little props to show you about that. So I see Chris out here. So I'll point it right at Chris, or I'll point it up in the back at the projector. You can see the light here? Okay, now this is a nice piece of tin foil, which is very, very good at conducting electricity. You put the tin foil in front. Does the light get through that? No. Okay, so we have to have a solar cell. Oh, I got to point that. There we go. We have a solar cell in which the light has to come through. So we're going to talk about that as one of the technologies being developed here. But for now, just allow me to say that we can create a material in which can conduct electricity and light can get through. So now the light can come down. I love my little thunderbolts on this. Comes down, and when it comes into the jelly of your peanut butter jelly sandwich, it gets captured and creates a little charge cloud. Okay, and that's the magic of the materials we're going to talk about. That charge cloud then migrates, and this is in a particular type of solar cell, which is an organic solar cell. We'll talk more about that. But that little charge cloud migrates. Let me go back and start it again. That charge cloud, if it ever shows up again, whoops. It's not good for the dean of engineering to be technically challenged. There we go. Okay, so the charge cloud, it has to migrate to that border between the peanut butter and the jelly. And when it migrates to the border, then it gets separated into the positive and negative, and you create a current. Okay? Everybody got it? I'm getting some nods, so I think you get an idea of this there. So, given that as the model of our solar cells, the challenge that we heard about is that we need to have high efficiencies in our solar cells and also be able to manufacture them very, very cost effectively. So the efficiency really comes down to two characteristics. The first of these is we got to capture all the light. All the light that comes in, we have to make sure that it can be used for creating electricity. The second is, for every amount of light that you capture in, per unit light that you capture, we want to make sure you get the most electricity out. Those two pieces are what define a very highly efficient solar cell. Okay, so we will talk about two alternatives to the types of solar cells that Annemarie was talking about in the first part of this. So the first one of these is the one I just alluded to, which is the organic solar cell. And what do I mean by organic? Well, you're not going to find it in QFC next to your organic peas and your organic carrots, okay? What we're talking about is something that is made from carbon-based polymers, okay? Plastic, the simplest form. So you'll see on the left and in some of these the chemical symbols for this. Anybody know what the chemical symbol, what the big thing down the bottom is? None of these guys up front are allowed. Anybody know what the big thing down the bottom is there? A buckyball. Fantastic. Exactly what it is. Okay, so these are made from polymers which are assembled, but are done in such a way which have these two characteristics. Number one, very efficiently capture light, and number two, very efficiently change the light into electrical current. Okay, so let's talk about capturing light. How do you want to capture light? So this is what hits us. This is those terawatts upon terawatts of energy that comes in, which is from the sun. So the sun produces a broad spectrum of light, ranging from down around 300 or 400 nanometers up to 1,200 nanometers. What does that mean? What it means is, first of all, this one piece, which ranges from about 400 to, roughly 400 to 800, which is the visible light. That's the way I see you, you see me, okay, is within this. However, you can see that there's a lot of energy out there that is in wavelengths that you can't see. That's the infrared. And you hear about that, infrared energy. There's a lot in there. So one of the tools which Professor Jen and his group have done is design sets of jelly, and actually peanut butter and jelly, but they're all slightly different. And what does each one do? Each one can absorb light at different wavelengths very efficiently. So you have one, and you see the chemical symbol below, which absorbs light mostly at the shorter wavelengths, in the blue and violet. You have a second, which absorbs mostly in the central wavelengths around green. Even though it's got double peaked, it's primarily in the central range where it does it. And you make a third, which captures some of the red, but goes way off into the infrared as well. And so you capture as much of that solar spectrum as possible in a well-engineered device. How do you do it? You make micro peanut butter and jelly sandwiches, which is you can put these and stack them together in multiple cases where, when the light comes in, the first layer will capture those short wavelengths, the second one's the mid wavelengths, and then the third one's the long wavelengths. And then the trick, which is the trick from Professor Jen's group, is how can you assemble those together to effectively get the charge out and produce a solar cell? So very effective method, again, all done by the engineering of specific organic molecules. Second one we'll talk about is Professor Christine Luscombe, who is in the Material Science and Engineering Department as well, and also jointly appointed to chemistry. By the way, that's a theme you're going to hear a lot of. Chemistry, material science, chemical engineering, chemistry. People are really not worrying too much about which department they're in, they're really worrying about what technology and science that they work on. So here's that conventional solar cell. And again, and we'll just play a few times. And one of the things is, I told you that you have to get that charge cloud to a surface, right? To the surface between the peanut butter and the jelly to get the electrons. Unfortunately, not all of that charge cloud can make it. And the farther you are away from one of those surfaces, the less likely you are to make it. You get it? So you're going the long distance, less likely you are to make it. So how can you do something to enhance or to reduce the length that that little charge cloud has to go before it's converted to electrons and holes? Well, you don't have a flat sandwich, right? Is that you structure it, except this structuring must be done down at a very small scale, back at a nano or molecular level. You have to structure that so that when the little cloud is made, there's a surface very close to it, so it does not have to migrate very far. Okay? So how do you do something like that? And you can do something, if any of you have raised children, you've seen them make peanut butter and jelly sandwiches sometimes, which are really not smooth. But how do you do it in a controlled way and an efficient way so that you can actually get more charge out? Well, you can do it by growing, and you're going to hear this phrase, and you've heard it tonight, molecular engineering and science, okay? And they're two of the major guiding principles in molecular engineering and molecular systems is directed growth and self-assembly, okay? Directed growth and self, and this is an example of directed growth. And what Professor Luscombe and their group have done is take a dot, and these are just gold dots placed on a substrate and done at a very small scale, down to nanometer scale, but then she does some gardening. And the gardening is that you seed them first, and what the seeds do is provide the seeds for directed growth of a polymer. So she can have this growing up in fingers like that. You say, that's very interesting. How does that get me that jagged surface? Because if I do that, I can pour another polymer back into the holes, and I get that jagged surface with the regularity that you have with the spacing that's there. Very well-controlled process, very straightforward, and produces much higher efficiencies in doing this. Okay, let's move on. So David Ginger, Professor David Ginger, who's in the Department of Chemistry. And what he's done is, among a number of things, is develop some technologies to allow us to see what's happening inside the solar cells. Now, here's a problem that is common to many areas of science and engineering. If you look at the left, what you'll see is a couple of solar cells. And you shine some light on them and you get some current out, and you say they're about this efficient, right? That's analogous to what you do by looking at the highway system in the state of Washington. And you see the highways, and you go to WashDOT website or something, and you see, oh, it's green everywhere. Oh, I got these red areas which are clogged and congested. What's going on? To do that, you must zoom in and go down to a smaller scale to see. And this is not a congested spot. Obviously, this is an open spot. But if it was a congested spot, maybe you'd see there was an accident or something like that, so you'd know to do that. Can you do the same thing down with the solar cells? The answer is yes, you can do that, but it must function down at this nanoscale. You must be able to make pictures at the nanoscale. What you see there is the bright dots versus the dark dots. The bright stuff is where the solar cell's really working well. And the dark areas is where it's not working well, very well at all. So why? Is there a traffic jam over there in that area? That's what this type of imaging allows you to do, and it allows you to optimize not just an individual molecule that works, but real devices. And so you can try to bring these into potential commercial. How do you do it? He leverages off a 25-year-old technology now called atomic force microscopy, which gives you this ability to look molecularly, but includes in it an ability to measure the current at point by point that is within that solar cell. So you can know now at individual, not quite individual molecule level, but down at that level, the nano level, what individual parts of the cell are doing in order to optimize your process for producing the cells. Professor Xiaodong Zhu. So, remember this problem, right? I don't have to do it again, right? Okay. So we have that in there. What he has been looking at is this challenge of how can you make this transparent electrode. That is something that gets light through, so it conducts electricity very, very well. It's transparent, and as we see, normal metals are not. But we got these two other features that we have to add to this to even complicate life. First, it's got to be cheap. And the second is, it's got to keep out oxygen and water. Why? Why? Why, Matt? Oh, sorry. The reason why is these things are out in the field. You stick them on your roofs. All right? These are exposed to environmental conditions. And so where the most likely causes of impact will be oxygen and water. Okay? So these are the characteristics that we want for art. So how do you do it? So all of you tonight can be involved in this technology because you were given a pencil. Right? You all have your pencil with appropriate websites on it, please? Note. Okay. So you have your pencil. If you just rub your pencil on this page, what you've put down is graphite, is a layer of graphite, right? If you could make that a single molecular layer thick, it's called graphene. Graphene is an amazing characteristic. So if you look at the top, it starts with graphite. What you see down the bottom on your lower left is literally the first measurements were made with the Nobel Prize, 2008, 2009 Nobel Prize in chemistry. You should be able to help me, John. It's in physics and last year. Okay, close enough. That was in there. But the way they got the first time, they used tape and pulled off a single molecular surface. It's not a lot more sophisticated than that now, but the idea is to reproducibly be able to have a single layer, a single molecular layer of graphite in this graphene structure. Conducts electricity better than copper or silver. Okay? 97% transparent, only 3% of the light is lost. Is dirt cheap? Right? Okay? And is impermeable to water and to oxygen. So what does it look like? It looks like this. It looks like this single molecular sheet laid out, which then can be placed into as an electrode. When in this position, it keeps the oxygen and water out. Those are universal symbols, by the way, for oxygen and water up there. But the light can get through. Okay? A remarkable technology that we're going to see much more of as we go through. Okay, next is Professor Hugh Hillhouse, who has just joined us this year. He is in chemical engineering. And he has been looking at the second major alternative to silicon-based solar cells, which is thin-film solar cells made of inorganics. And what we're going to talk about is the future, but what we really want to impress upon you is that thin-film technologies are now. okay? And the example I have is from Germany, right, Hugh? The one on the left up on top there, which produces over 50 megawatts of power and is 64 times the area of Husky Stadium. So this is not exactly a small installation that's in there. However, it's all rolled out as a sheet, as you can see on the panel on your right. So it's a wonderful technology, relatively high efficiencies, relatively easy to install, as you can see up there. However, there are still some challenges for this current technology, and that is it contains rare elements, which means it's expensive, so there's major scaling issues. It has less expensive to manufacture, but still not at the cost target some of the ones that Anna-Mari showed that we required for this to be economically viable. So what's Professor Hillhouse doing about it? Well, he, again, is doing the molecular engineering approaches to this, where in effect what he's doing is he makes ink. So the central panel, you can see the little tube in there, that's actually ink, and to the right at the top you can see the droplets that come down that are formed. But by, again, molecular engineering the design of these inks with nanocrystals in them, that when you lay out the ink in exactly the same way that you would print newspaper, or very similar to the way in which you print newspaper, the second principle of molecular engineering is self-assembly, is that these particles will assemble, as you see in the lower right, will assemble into a structure which is a thin film photovoltaic, which then, once it hardens, you have devices which literally can be printed out there. These also, and this is some of the work he's working on, is trying to change the types of materials which are used in these devices so they're naturally abundant materials, in particular replacing some of the exotic rarer elements with copper, zinc, tin, and sulfur, which are in very high abundance around the world. The goal for this is to do, again, what Anna-Mari was talking about, is to reuse our printing presses. We have a little family thing. My wife's a newspaper reporter, ex-newspaper reporter, because her old paper is defunct. And they have a beautiful press, which I'm thinking of as a development opportunity for this technology. But it literally is the same type. It can produce cells of a type such as this, this is a commercial one from Konarka, but this is a solar. And when you think of solar panels, right, you think of these very large, bulky things you install. Oh, these guys in front are cringing whenever I do this. Okay? It is so flexible and easy to use, you can place it in things like put it in your backpack. All right? So you can charge up your iPhone or your iPad or your whatever to do that. Very, very interesting technology, and also with the idea of being able to print, to be able to go to printing, scalable and cheap. Also, too, I have to mention in passing that the organic cells that I also talked about are printable. So fundamentally, the two technologies we talked about are printable technologies. As a result of that, the scale-up is possible, because the same types of things that are done in producing saran wrap, newspapers, film, those types of things can be applied to this technology. Okay, let's move on over to the storage area. In the storage area, Guozhang Chao, who is a professor of material science and engineering, has developed a very interesting technology that applies to this time of day, namely that how do we use the charge that's there. Well, for energy storage, you can convert the electricity back to fuel. That's a very efficient, actually, way to store energy, but kind of counterproductive. The best way to store charge directly is by using batteries. But batteries have problems. Okay, they're energy density. You cannot store a lot of charge in conventional batteries in reasonable volumes, which can create issues when you're trying to use it for practical purposes. Also, too, when you use it, you discharge it, which means you have to charge it. And that can take considerable time given the current battery technologies. What Professor Chao's group has worked on is a new technology using molecular engineering nanoscale devices, which if you look at your old capacitor on the left, it's just a set of a lot of sheets which are immersed usually in an oil of some kind, of dielectric. So they have this immersion that's in their sheets. So Professor Chao's technology, which is on the right, is the same thing. It's all sheets, Same type of thing just wrapped around. Except when you look at it down at this nano scale, it's structured. Remember Professor Luscombe's thing with the fingers? It's the same kind of concept, if not the same exact technology, for structuring the 3 minutes so you can store charge everywhere, not just on the surface of the sheet. Very rapid storage capabilities done in carbon, and also can be charged and discharged very, very rapidly. That technology has gotten a lot of press recently and has been the basis for a startup company, Energy 2, which is in the ultracapacitor business and has gotten some major investment in about the last year and a half, and one of the first spin-out companies from these technologies. Okay, last one in storage is by Professor Dan Gamlin, who's in the Department of Chemistry, and he's technology, it can be used for storage, but also it's a source of energy. So it's an interesting technology that combines both the source and the storage. Here it is, and the idea is exploiting hydrolysis of water. Sounds like a fancy phrase. We all did this. We all did this back in either in high school or as kids. But the idea is you stick a current into water, and you can separate the two pieces, the hydrogen and the oxygen, to get hydrogen gas and oxygen gas. Okay. Usually, at least in my time when I was in high school, is you go for the oxygen because you get to breathe the oxygen. But it's the hydrogen that if you took a match to, well, anyway. But hydrogen is a very efficient storage mechanism for energy that can be used and burned at any time. The way in which this is done, though, is you replace the normal electrodes that you would have in conventional hydrolysis, and you have a photocatalyst, so the light's energy comes in, that creates the source for hydrolyzing water. So photocatalysts, the problem is that the current photocatalysts are way too expensive, platinum being one of the major components of that. So Professor Gamlin's technology has turned a bug into a feature. And that is that if you can engineer rust, good old-fashioned oxidized iron, the rust that we all try to get rid of on our backyard furniture, but if you can structure that down in the nanoscale, then it in fact becomes a very efficient photocatalyst for hydrogen production. So very, very interesting technology for both generation and storage in the form of gaseous hydrogen. So let's go to the last piece of this, which is about use and the efficient use of energy that's delivered to our homes, to our factories, and to our offices. And this is work of Professor Sam Janicki, who's in the Department of Chemical Engineering and also jointly appointed in the Department of Chemistry. So we know we need efficient lighting. Our incandescent bulbs are 10% in efficiency. All of us, I hope, are replacing bulbs as we use them up in our houses, incandescents, with compact fluorescents, but they give us about 35%. What we're looking at and what Professor Janicki is developing is technologies for solid-state lighting that can have efficiencies on the order of 75%. How do these work? Well, it's really pretty simple. In concept, in practice tough, but in concept it's pretty simple. That is, remember our old friend, this organic solar cell that we have on the left? Well, remember, light goes in and some electricity will come out. Okay? But what if we run it backwards, is the way to think about it. That is, what if we inject charge into this, we can engineer it such that light will come out. It's real. So you can see over here, Professor, this is lighting's a little bright here, but you can see on the left that glowing object on the lab bench there, Professor Janicki's in the back, but you can't see him too well. But anyway, the glowing object on the lab bench there is a piece of polymer that is your light source. Okay, so in the same way that you had this to create your energy, you could have the back of it as a beautiful light source that you could use. Okay? And in fact, people are starting commercially to look at these technologies for doing precisely that. Everything from Boeing, who's looking at this as sort of custom cabin lighting systems, to portable displays, which you can bring with you, to what you see down the bottom, these sort of designer light sources, which you can integrate into every part of your life and your decor. So I think in this last 25 minutes or so, I've tried to give you just a very broad brush of the types of work that are going on here at the University of Washington. And it's both broad and deep, meaning that we have a lot of people working in the various aspects of energy generation, storage, and efficient use. What we're interested in, and what Anamari is going to finish up the last few minutes of this talking about, is how do we take this tremendous collection of people and facilities that have come together over the last 10 to 15 years, and what can we do institutionally to transform this into the University of Washington have true societal impact in the area of solar energy. So, Anamari, I'll pass it off to you on this.
Always cleaning up after Matt. Now, I come from Miami, and so when I tell my friends the Pacific Northwest is just the perfect place to be doing solar energy, they look at me a little cross-eyed. But, you know, in the Pacific Northwest, we hike, we go out to the mountains, and we make really good peanut butter and jelly sandwiches. And we really are. We have right here at the UW, together with our partners at the Pacific Northwest Labs, we have formidable capabilities to bear on the core technology on areas such as nanophotonics and catalysis and their applications to solar energies. Matt told you about this octet of faculty, but we have an amazing team. We have over 25 faculty members and about 100 students, graduate students in arts and sciences and engineering alone that are working just on areas related to solar energy. Together, this team was able to secure over $50 million of grant support in the past 3 years alone. That includes support for 2 centers that are funded by the National Science Foundation. We've had scientists that have gone to the White House. They've won awards from the Sloan Foundation, from DARPA. They're fellows in the American Academy of Sciences. Our team really is world-class. Now, what we're trying to do is make sure that, oh, there's our team. What we're trying to do is make sure that we also have world-class facilities so that they can do their work. For that reason, groundbreaking for the Molecular Engineering and Science Building, MALE, was held in fall of 2009. I hope that as you drove in, you saw the cranes, and you can see that we're about to open the building January 2012 with 90,000 square feet of state-of-the-art research labs and instrumentation space. I can't wait. It really looks beautiful, and it almost looks ready to move in. Molecular engineering and science is a field that's associated with the design, manipulation, fabrication, and delivery of functional macromolecules and molecular systems, and they can be used for medical, energy, electronics, photonics, and a host of other societal applications. We often employ MALE approaches to tailor the size, shape, sequence, and functionality of organic hybrid functional materials, and to explore the many applications. And that's exactly what we need to move this whole area of photovoltaics and solar energy to the next level. Pat Stainton was named as the Institute Director, and he's heading up one thrust of the work to be done there. And that's going to focus on the life sciences, which is another area. We could give another talk on some of the work that's happening at the interface of engineering and arts and sciences. The second thrust is energy. And central to this energy thrust is another institute, the Advanced Materials for Energy Institute. This institute pulls together basic and applied research as well as outreach and commercialization, all focused on the energy area. The scientists and engineers in this institute are going to be working side by side in the new MALE building on exactly the kinds of problems that Matt just talked about: the generation of energy, the efficiency with which it's done, and on storage and distribution. And we're really excited to have them move in and continue this work, because I hope we've convinced you that it's really important. So now I'm going to turn things over to Jack Farris, who's been so instrumental in helping us put the program together tonight, but also this program of research more generally. And he's going to be introducing you to our fabulous panelists and moderating a discussion and some questions and answers so we can tell you a little bit more about what's going on. Jack.
Great. Thank you, Anna Marie.
All right.
High technology. We've been working on this event for some time, and inside the planning team, we've been referring to the presentation that you've just seen and the people who delivered it as the Dean team. I think they're a pretty remarkable team. Let's give them a hand again, please. And the majority of the octet that Matt O'Donnell talked about are actually here in the front row. And if questions arise from you, and you're all invited to submit questions, that they would be better equipped to answer than certainly myself or even our deans. We'll put the questions to them. They're here, and a number of students and other folks who work in all kinds of functions to support this work are an important reason for hoping for the future. And so I'd actually like to invite everybody who touches this technology in any form who's here tonight just to stand up for a second, and let's see how many of you are here. Please stand up, folks in the front row for sure, but there's others. Look at this. How about that? We definitely seek to encourage you in your work. Thank you for being here. Now let me invite my very distinguished panel up, and as they come up, and I'll begin to introduce them. So panelists, please come on up. I will apologize in advance to each of them for any occasional outbreaks of rudeness on my part. I'm going to try to keep things moving rapidly. We're going to conclude pretty close to on time, if not right on time. And so if I feel I need to, I'll break in and keep things moving. Let me introduce from my left, moving this way, the Dean of the College of the Environment here at the University of Washington, Dr. Lisa Gromlich. Next to her is Dennis Hayes, President of the Bullitt Foundation, and then Rick Lefebvre, who works here at the University of Washington on technology commercialization, and also on the other side of the fence with OVP Venture Partners. And lastly, Susanna Malarkey, Executive Director of the Technology Alliance. I'm going to ask each of them one question. I'll invite them to ask questions of each other, and then we're going to start to hear questions from you folks. So if you want to write it on cards or send tweets or Twitters or whatever those things are, please do so at any time, and we'll get to as many as we can. So I'm going to start off with Lisa. A comment, if you would, on the significance of what we're talking about here from your perspective as Dean of the College of the Environment.
Thank you, Jack. First of all, I think the presentation by the Dean team captured a lot of the excitement of this emerging technology and the leadership position that UW plays in developing those technologies. I'm the Dean of the College of the Environment, and what I'm here to say is that there is, beyond the excitement, a high degree of urgency that we actually move forward rapidly as possible in developing these renewable energy options. And I was so pleased. I had many ideas about how I might approach this, and I was going to talk about why the burning of fossil fuels and the CO2 that ends up in the atmosphere is one of the environmental impacts that was touched ever so briefly in Anna Marie's presentation. And in thinking about how to talk about that, you're thinking, oh my gosh, she's going to like talk about global warming for the next half an hour, and I'm not even going to say those words again. I'm instead going to say something that I think those of us in the Pacific Northwest should be very, very concerned about, and my colleagues from NOAA were featured in today's Seattle Times talking about what at times is referred to as global warming's evil twin, the notion of ocean acidification and the fact that that excess CO2, it used to seem like it was a great thing. About a third of it goes into the ocean. You know, we can drive more SUVs because CO2 is just going into the ocean and kind of buying us some time. But what we have discovered, in part through UW scientists and their collaboration and the leadership of our NOAA colleagues, is that that increased CO2 in the ocean leads to an increased acidification of the ocean with very, very dramatic effects on everything from the smallest of microorganisms to larger and larger food webs, and eventually up into some of our most beloved and charismatic marine mammals. So read your Seattle Times on the web or in paper to learn more about this, but to be aware that when we talk about the urgency of it, it's particularly urgent for those of us that live in the Northwest. It turns out our ocean waters off the coast of Washington are already older waters that are upwelling. They're 2,000 years old, my oceanography colleagues tell me. That makes them more corrosive to begin with, and so this impact, the bullseye of where this is going to hit first is in our backyard. And that should make us all the more motivated to move forward with this technological innovation. Thank you, Jack.
Thank you. Thanks. Yes, thank you. So I'm going to jump over to Rick, who brings a very hard-minded commercial perspective to these technologies, and invite his comments on, so why should we get interested in doing this from a more of a local community perspective? Rick?
So my job is to talk as an investor a little bit. I'd like you all to pretend that you're an investor looking for the next great deal. And investors are always looking for paradigm shifts. You're looking for some technological breakthrough that causes a disruption and then over some period of time causes a new order to emerge. And if you think back in history, I guess the Industrial Revolution, the invention of the steam engine was one of those, the rise of trains and planes and automobiles and electricity and antibiotics and vaccines. There's been a handful, probably not as many as you might think, that really had a fundamental impact on mankind. I think in my life there's going to be three of them that I'd like to point to. One is the rise of the computer and the internet. I lived through that. I've got more compute power in my pocket right now than the main campus computer that I worked on when I started as a student in the 60s. It's been a fundamental transformation in all of our lives, and I won't go into that because that's not the topic tonight. But it's played out over, 30 years? If you think about from the rise of the original ARPANET to where we are now, with mobility in the cloud being layered on. Transformational technologies. People that invested at the right time made a lot of money, as we all know, in that space. The second, I think, is going to be the rise of genomic medicine and personalized medicine. And that kind of can be traced back to the turn of the decade when we decoded the human genome. And it's going to transform medicine over the next, again, 20 or 30 years. In that case, we're kind of in the middle of that tornado. OVP, about a third of our portfolio is in digital biology, which is very, very exciting. The third, and the reason we're here tonight, I think, is going to be the transition to clean, renewable energy sources. I think in that case, we're at the very, very early stages. I get asked by some people, gee, I read about something happening down in the valley in energy. Are we too late? And no, we're not too late. This is just starting. I think over the next 30 to 40 years, you're going to see a fundamental transformation of mankind based on the kinds of things we talked about today. And I'd like to point out that in all three of those revolutions, the Pacific Northwest, Washington, Seattle, UW, had a major role to play in terms of the creation of the Information Society, in terms of what's happening now at UW and the Hutch and ISB in personalized medicine, and the kinds of things we're talking about today in terms of the transition to clean energy. So from an investment perspective, It's not a coincidence that if you look at the venture capital investment trends, the top 3 investment areas are software, biotech, and clean energy, with clean energy and biotech actually kind of fighting it out for 2 and 3 if you look at kind of a quarterly basis. So it's an extremely exciting time. Lots of bets being placed in this space, lots of bets on solar energy in particular, as the long-term answer. And so I think we're very well positioned here to really drive this thing forward, and it's a very exciting time to see it play out. So.
Great, thanks, Rick. And Susan, yeah. They all get one applause at the beginning, and then we can have one at the end, but I want to save plenty of time for your questions. Susanna, picking up on what Rick was talking about, we are not Arizona. We don't get as much sunlight, but we've got some other assets here. From your perspective in the Technology Alliance, which has done so much over the past 16 years or so to advance technology broadly in our state and in our region, what are the kind of things that you think will be important assets for us to approach these opportunities from a kind of an ecosystem perspective?
Right. It's interesting. When we started the Tech Alliance 16 years ago, we went and visited each different regions that were successful, and we began to sort of sort through what does it take to be a world-class high-tech region. And the most important thing was to have a world-class research university. And that's why we at the Tech Alliance have worked so hard over the last 16 years trying to help the public and legislators and opinion leaders understand the absolute critical nature of having a world-class research university, and that UW is this incredible asset that we need to take care of because in many of our peer regions, they have a private research university that is also part of the mix, and we don't have that here. We don't have MIT, we don't have Stanford, we don't have Duke, we have UW. And so that's been the number one thing that I think we have to understand. I mean, obviously this community gets it, but we have to help tell that story, and because UW is really under siege right now in terms of public support, and so in order to have the kind of infrastructure we need to get this work done, we have to protect and strengthen UW going forward. I mean, that's really the number one thing. The other kinds of things you need are smart money, and you need a great entrepreneurial climate, but the research university is number one. And I think a lot of times when people think about what makes a research university great, the first thing they think about are the faculty, and they think a lot about commercialization of technologies. But honestly, the most important thing that University of Washington does for this region is educate amazing students that go out and start companies and do their work and become employees of the companies that are already here. And so I think we need to really remember that it's also the students. It's not just the faculty and the companies we create. The incredible asset that will grow this region is great, great students.
Marvelous, well said. Thank you. And then fourth, to Dennis Hayes. I want to preface this by noting that one of the central premises of this evening and this work is that that these are real opportunities, but also that we can move toward them at a not predetermined rate of speed, and we'd like to see it move faster. You've been an observer and active in this environment for more than a couple decades. What are the lessons learned, do you think, that both successes and failures that should inform how we think strategically about how to maximize the pace at which we could develop these potentials?
Well, thanks, Jack. Like the others, let me say that I was awed by the presentations tonight. We didn't get to the depth, though I know Matt well enough to stipulate that the depth is there. The breadth is obvious. And I had no idea that we had that kind of program at the UW, and I think it's enormously impressive. Had I had any idea what the program tonight was really about, I would have declined to serve on the panel. Because this is the topic that I've devoted more of my professional life to than any other, and you have never seen a more abysmal failure than my life on this topic. I jumped into it in the early 1970s because I really wanted to become invested in some of the issues that mattered in the world: war and peace, racism, inequality of wealth, energy, and boy, energy was relatively obvious. You saw what the problems were, you saw what the solutions were. Big hurdles to go through technologically, but handleable hurdles. By 1975, we had not got all of the work done that you've done on organic solar cells, but every other photovoltaic technology that's commercially available in the world had been developed here in the United States, mostly with taxpayers' dollars. We were kind of ready to roll, and in fact, I was pretty instrumental in getting the President of the United States to declare a goal of having 20% of the nation's energy from renewable resources by the year 2000, and of devoting a year and a half of my life to heading a multidisciplinary, multi-university, multinational research laboratory effort to map out how you get there. And he lost the election. And within 6 months, we dismantled the program, and my laboratory lost $100 million a year, and about 60% of its staff and all of its contractors, 3 of whom went on to win Nobel Prizes subsequently in other areas. And on and on. We had strategies, Jack, that respond to your program, and part of it had to do with some of those cost comparisons that we were talking about. Those are phony costs. I mean, sure, you can say that coal costs a certain amount because we don't internalize most of the costs of producing coal and virtually any of the costs of combusting coal. We don't internalize the cost of keeping a fleet in the Indian Ocean. On and on. You know this litany. And so there were many ways that you could try to get that done. We have had a remarkably poor job of doing it. In nuclear power, exactly the same thing. There are 60 reactors under construction right now in the world. There is not one of them that is being brought to market by a free market. Not one. The subsidies run up approximately to 100%, coming from public funds that no market would be touching. And that's even when you've got such subsidies as the Price-Anderson Act that says that if you have another Fukushima here in the United States, there's a strict limit on the liability of the people who build it. If they had to buy private insurance for that, it would price them entirely out. So on and on and on. It's a series of terrible price signals. And so one thing you try to do is work with public policy to change those price signals. Progress has been non-existent because there are various states that care deeply about each of those technologies, and they've fought hard to get it done. I suppose, and I say this with a degree of optimism, a degree of regret. I don't have any hope at all for Washington, D.C. at this stage. Literally at all. There are some neat things that are going on in states and regions. Jerry Brown, bless his heart, Governor Moonbeam, has just today signed a 33% solar goal and a whole series of policy initiatives for the state of California. 33% by 2020. That's a fairly ambitious goal. And I think that begins to create a market for a whole lot of the things that we've been talking about tonight. And I would love to see something akin to that come in a number of other states that have historically sometimes been a few months behind California. And those of you who are close to the governor might want to suggest it. The real answer, though, has to do with tipping points. And they are pretty much unpredictable. Is there anybody in the world a year ago who expected North Africa and the Middle East to become cauldrons bringing about a revolution to install various levels of democracy? Yeah, one I was deeply involved with was the first Earth Day in 1970. What made it possible? It was somehow we were dropping a crystal into a supersaturated solution, but I, to this day, don't know why there was such an enormous amount of responsiveness. I mean, we didn't have the internet. You know, we were dealing with mimeograph machines and telephones. And we got 20 million people out on the streets in a matter of about 4 months. It was ready to roll. There was the Santa Barbara oil spill. It was nothing. I mean, trust me, the Santa Barbara was like 700th on a list of major oil spills. The Exxon Valdez is 57th. I mean, there are a lot of big oil spills, and this was not one. But something becomes possible, and it happens. That has happened today in a few places in the world with regard to renewable energy. I think it may be on the crest of happening once again in California, which was out there in the 70s as well. But the one place where it really is there is China. The commitment is formidable, and they went from leading the world in no renewable energy technology 5 years ago to today leading the world in the 5 most important renewable energy technologies. And that's not just with cheap production, that's with major investments in fundamental research and development as well. And my hope, I suppose, in terms of the United States, and I apologize for giving a lecture instead of an answer, but my hope for the United States is that what we are best at, and I hate to say this, but nationally, is not in taking the initiative, it's as a counterpuncher. You have Pearl Harbor. You know, we dawdled around in World War II for 7 years, but Pearl Harbor, and boy, did we mobilize. You have Sputnik, boy, did we mobilize. And we've been talking about renewable energy. We've had on. If China suddenly continues to increase its photovoltaic production by 200% a year for another 2, 3, 4 years, at some point we wake up and I think we begin to change those price signals, and suddenly you've got an environment where every investment that you make that's halfway intelligent is going to make you rich.
Oh, halfway intelligent. Well, hold it now. Can I make it?
Rick, we're going to ask you to comment, but first, Dennis, I want to say that I'm happy that we were able to mislead you into coming here tonight. Rick?
Just a follow-up comment on China. I'm on the advisory board for the energy group at PNNL, which is doing some very interesting work in areas like carbon sequestration and other areas. They are actually getting more pull from China to partner than they are from in the US. So Mike Davis, who heads up that organization, that directorate, is spending a lot of time in China working with the Chinese because, hey, it's a global environment. And so getting Chinese carbon capture under control, et cetera, is good for all of us. And so they are very serious. And they are reaching out to partner with people in the US to try to figure out how to attack these problems.
And they're moving more aggressively than anyone else is into some of those technologies that make it easy to capture the carbon as well. Yeah. No, there's something to be said for a government that's run by engineers. Mm-hmm. I hope that's a popular thing to say here.
Susanna, would either of you like to make a comment or ask a question of any one of the other panelists?
Well, I just want to echo Dennis's thought about the tipping point. Like, what is it that creates a tipping point? And I think that, there's global things going on, but I also think that there's local and regional things going on. And so I think that for this region, we are among the regions of this country, I think, the most aware of sustainability. We have a good tradition of energy efficiency in the built environment. We have these assets that I think we can use in terms of having an educated populace that's more inclined to do this kind of work. And so then I think it's really incumbent upon us to raise the level of awareness to the state level and begin to have more state policies that help get us to that tipping point, because I think that we really are, we have some competitive advantages, and I think we need to really challenge ourselves to take advantage of them. So I think we can kind of push that tipping point ahead with a little bit of focused effort.
Dennis?
You were first. I've been talking a lot.
You go and then I'll go.
Just watch the cards
Well,
coming in.
in a sense, I want to follow along on a prepositional phrase that Anna Mari had in the course of her talk. And it particularly leads to the kinds of PV technologies that the university appears to be placing its principal emphasis on. And it goes back to my original dream, actually, back in the early 1970s. If you go to the area where there was that huge eruption of Mount St. Helens, for years afterwards, it was a moonscape. There was essentially nothing there. And then slowly, it began to come back. Little things, lichens, moss, eventually built up a bit of topsoil, and then some grasses got into it and built a bit more turf, and then ultimately some shrubs and some trees. And you go to much of it today, and it is covered with life, and in fact, fairly rich, diverse life, all of which was powered by solar energy. It was an area where there was nothing to harvest it, and stuff went in and began to accumulate it. The comments that she was making about rooftops being fertile areas, I'd say rooftops and south-facing walls and the south sides of north-facing billboards and all sorts of things that point toward the sun. If you've got things that are flexible, can be easily shaped over different objects, essentially plastics, I think, and if they are cheap and if they've got a reasonable level of efficiency, That's a place where I think we can really have an enormous impact. Where my vision of the future has always been that a form of photovoltaics would do for human energy what photosynthesis does for the rest of the natural world. And that's pretty tough to do with silicon, but it's not that tough to do with all of the technologies that you're working on.
Yep. Lisa.
I just am going to reflect for a short, less than a minute, that a joy of moving to Seattle in the last year is the kind of engaged audiences that we get at events like this. And I want to make sure that those people that are sending questions down get a chance to have those questions be heard.
So I'll jump right into a question. And these, of course, are going to come from literally all across the room and from a variety of perspectives. I think this is a very interesting one. What happens to these solar cell nanosubstances when they enter the environment, and can they easily be recycled? I don't know if we have any volunteers up here, but I'm sure we have some folks down here in the front row who could respond to that. Hugh, go ahead. So Mike, coming over.
Well, I can't speak on.
Mm-mm.
Okay, so I won't say anything about nanosubstances, but a lot of these materials that we make solar cells out of. Is this on now? Yes, okay, great. I can't speak about any of these nanomaterials. These are things that are technologies that are just being developed at this stage. But a lot of the new technologies, a lot of the new solar technologies out there, companies actually offer to take the solar cell back. So it takes this out of the public's consideration, and that's taken into account as part of the life cycle cost and analysis of the solar cell. So that's what I would like to see also for new technologies, that basically that thinking about what happens to the device at the end of its life is part of what we as scientists and engineers get good at, making you not have to worry about that.
Great, and a great question.
It's worth saying also that with regard to some of these things, they are toxic. And so, for example, First Solar, which has been hugely successful in Germany, was only able to penetrate the German market for a cell that contains cadmium if they were able to assure the Germans that they would recycle 100% of it. And that forced them to develop a recycling program that otherwise might not have come along.
This next question is, what kind of energy does the grid system waste in transmission distance? And I imagine that means what kind of magnitudes is lost in transmission? That, again, might go to the front row. Or David. It's David Ginger.
I think the answer was going to be quicker than the microphone took to come on. It's 7%. I think the grid delivers 93% of the energy that we get. But the problem, I'm not a smart grid person, the people in the electrical engineering department who do smart grid could tell you this, is it's not very good at balancing and handling loads. And so intermittent renewables that deliver during the day or that come on when the wind blows need a grid that can properly switch on and off and redistribute electricity. So we get what the coal-fired power plant is delivering with 93% efficiency on average, but we need it to be able to operate in real time and switch loads and balance better.
Great, thank you. Here's one that I think could be the subject not just of an evening, but a whole semester. I guess we have quarters here. Explain the potential pricing and competitive market factors of solar energy.
A couple of just random observations. One, there are a whole lot of different kinds of grid losses that can occur depending upon where the power plant is, how it's operating, and what the demand is here. And some of the numbers that you see are substantially higher. If the solar is on your rooftop and you've got your power conditioning there and your inverter, then you don't have any line losses. So that torques those price figures a little bit. Second, we talk a lot about how you store the sunlight from the day so that you can use it at 3 o'clock in the morning, but the real thing is that most people were not designed to work at 3 o'clock in the morning. Mm-hmm. And a lot of people on midnight shifts would rather not be. But because the power is cheaper there on some kind of a power source that operates as an around-the-clock even production, tends to force industrial processes into directions that they might not otherwise go. If you take a look at what we are currently doing with conventional economics and conventional financing for a really efficient solar array in Arizona today, it's probably on the order of about 14 cents a kilowatt hour. That's 14 cents for a kilowatt hour at sometime between 10 o'clock in the morning and 3 o'clock in the afternoon in Phoenix. In Seattle, that's going to be more like 25, 26 cents. Both of those are going to be competing against some kind of a peaking unit that will be like natural gas that fires up to meet that peak demand in Arizona. It's an air conditioning peak load there. And it's pretty close to competitive today. It's just wrong to be comparing something that is available at a particular point in time where it's displacing something else that's an intermittent source with a base load. It's never going to be, well, never is a big word, but to compare it against the cost of coal-fired production is just a little bit misleading. What is going to be competing with it is going to be a natural gas combustion turbine, where the prices are pretty uncertain into the future, depending on all kinds of issues having to do with fracking and relations with Canada and what happens with synfuels and on. But almost certainly it's going to be within pennies of being competitive without internalizing your environmental externalities.
So one more comment on this topic. There are some very innovative business models coming into play now. In the old days, in fact, for most of us now, you get your power from the power company, you pay whatever they charge you, and that's it. People are now going in and saying, how about if I rent your rooftop? I'll install a solar panel on your rooftop, and we'll split the savings that we get. I'll get some of it, you get some of it. And so there's a lot of innovation happening in this whole space now.
So there are some really great questions, and some of them have actually anticipated things we've already talked about, so, and I'm sure the people who wrote those will recognize that. Here's a very interesting one. What is the efficiency percentage that we think will tip solar? That, again, you guys might want to comment on that.
I saw a very complicated chart just yesterday, actually.
Yes. Well, I would say that it's not about efficiency alone. So it's really a combination of efficiency and cost. And I think what is near and dear to most of us is how much the electricity we get costs. And so that's one element of it. The other big element is how much energy it takes to make the cells, like Anamari was telling us about earlier. And so it's cost, it's efficiency, but it's also the energy that we dump into these things. And there is not a one unique number of efficiency that is the tipping point. There can be combinations of cost and efficiency and energy payback that cause it to be economic in various niches that grow and then basically take over and then supply large amounts of energy. So yeah, there's no one unique number.
That's a long way of saying it depends.
Well, and I think the other thing to remember is that it also depends on what the cost of fossil fuels become. I mean, so, and that's, and we've had, subsidized fossil fuels, and there have been, countries and regions and states, like Dennis was saying, that have figured out ways to incentivize solar. And, my brother I was saying earlier, my brother ran a company in Massachusetts back in the mid-'70s that 80% of their business was solar. But then when they changed the tax rebate law, all of a sudden it wasn't cost effective, and he lost 80% of his business. Only 10% of the people were going to do solar when it was going to be way, way more expensive. But when it was competitive with oil, lots of people would do it. So we can use public policy to help incentivize what we want to see happen more quickly.
And that sets up my last question. I'm going to combine two and ask each of you to comment briefly, if you care to, in response. The two-parter is, why are California and China beating Washington? And the second part, in the audience are representatives of local elected officials. What would you like to tell your elected officials or ask them to do to move our society faster to our solar future? Lisa, would you like to comment to start?
I think that there has been, in places where there has been more quicker and earlier adoption, the notion that Dennis brought up of understanding the true external costs and impacts of our current energy use have been more fully realized, and that we have been lagging behind in fully realizing that ourselves. And if there's a message to the elected officials, is that we've got to create the policy environment that allows the tipping point that is unpredictable to be closer to our horizon.
Excellent. Dennis?
I suppose for local elected officials, it would be to recognize that this is, in any poll that you will take of your constituents, this is the most popular thing out there. I mean, there's not wild enthusiasm for solar energy within the oil industry, within the gas industry, the coal industry, reluctant to say the electric utility industry. This is really popular with the public. That's why I devoted so much time to trying to change public policy, because I thought we could get the people to force their elected representatives to create at least an even playing field, and ideally one that would tilt it toward renewables so that we could accelerate this even faster. That hasn't happened, but tell your boss. And unfortunately, people want it, and they want it only weakly. It's not like abortion or gun control or something that they will vote only on that issue, but it is something you're not going to lose any votes at all by supporting. The other thing to say is actually the real problem, in my view, with penetration has been business model. We don't make our capital investments in anything except solar, right? You don't go out and buy a piece of a coal-fired power plant. You don't invest in a natural gas pipeline, but you're expected to pay 100% of the cost of this thing that goes on your roof, and to do the math to calculate exactly what your payback will be or what your rate of return on investment will be, to go out to some bank that is not used to doing this stuff and arrange a loan to do it at some cost that's not going to, an interest cost that's not going to be prohibitive. That's not a business model, I think, that's going to ever cause an explosive growth. We have to have some place where the big concentrated sources of funding in the society, pension funds, the government, other big things, utilities, to be investing on the customer side of the meter. And until we get that, I think it's going to be really hard to have explosive growth.
Very quick thought.
The leadership in both China and now California have figured out that carbon is expensive. That burning carbon fuels has unintended consequences. And I think you asked what we need to do from a political perspective. You know, figuring out some way to put a price on carbon, to drive an economic model that drives things, you know, towards renewable resources is going to be paramount. And I don't look to Washington to do anything intelligent in that area, at least for another couple of years, and then we'll see what happens. You know, so.
And Susanna.
Well, I do think that one of the best ways we can move things is to give people really great examples. And I guess, since I think I've got the last word here, I would really challenge University of Washington to think about the fact that you are a great test bed for new technologies. You know, this is an institution that uses a lot of energy, and it can commit to becoming carbon neutral by a certain date. It can commit to having the most innovative things going on here and really using some strategic philanthropy to fund that. And I think it would be great, I mean, because it would really show that University of Washington is leading the way and showing the rest of the state what the future can be. And so I think you guys should get on it.
That's a great, yeah. And Susanna, you'll be pleased, and I think everybody here will be pleased to hear that we are actually working on installing demos of these emerging solar technologies to show on campus, to show how it can contribute to solving our own needs. So before I ask you to join me in thanking the panel, let me just note we had way more good questions than we could get to. Answers to those questions will be posted on the Advanced Materials for Energy Institute website. So if you can just remember UW Advanced Materials for Energy website, if you didn't get your question answered or you'd like to see answers to other good questions, please check that out. And with that, please join me in thanking a remarkable panel. And lastly, it's my pleasure to bring up for just one more minute, to the lectern, the president of the University of Washington, who's just heard a strong exhortation, with a few words about how we can work together to realize these possibilities. Dr. Phyllis Wise.
Well, I know, Jack. I know you were supposed to do that, but in all honesty, this is so anticlimactic. Thank you so much for coming. It's wonderful, Anamari and Matt, for you to have given us the start of this wonderful symposium and for all of you to have participated. The most wonderful thing about being here is to be able to participate in an evening like this, where we are told what we should be doing, we're telling the legislators what they should be doing, we're also talking about what we're already doing. And so thank you so much. This is the beginning of a very important conversation. We are going to be investing even more in this whole area of energy, renewable energy, particularly solar energy, so that we can provide even more answers and then be able to commercialize them. So thank you very, very much.